Hello, my name is Joe Danby. I'm studying for my integrated Masters in Psychology and Psychological Research here at the University of Birmingham. And in this video I'm going to be breaking down an exciting new research study I'm conducting with Dr Hong-Viet Ngo and Dr Bernhard Staresina into the relationship between sleep and memory. Before I go into that though, first let's break down what we already know about sleep and already know about memory. Human sleep is characterised by two unique states, described as being as distinct from one another as both are from wakefulness. We have rapid eye movement, or REM sleep, a simple definition for which could be a state wherein we have an activated brain inside a paralysed body. Then we have non-REM sleep, which could be defined as the converse, an inactive yet actively regulating brain inside of a movable body. Non-REM sleep can be subdivided into three stages, stages 1, 2 and 3, with each passing stage having a higher arousal threshold, which is to say it's hardest to wake up from stage 3. Stage 3 sleep, otherwise known as deep sleep, delta sleep, or as we'll refer to it from now on, slow wave sleep, features something known as slow wave activity, slow high amplitude EEG oscillations. Normal human adult sleep begins with non-REM sleep, which transitions to REM sleep after 80 plus minutes. Thereafter, non-REM and REM transition between each other in cycles lasting for around 90 minutes. Over time, REM sleep starts to account for a greater proportion of that cycle, and slow wave sleep takes up less of the cycle, if not disappearing altogether. For this reason, the first third of the night's sleep is dominated by slow wave sleep, and the final third dominated by REM sleep. How important is sleep? It seems as vital as eating or drinking. Rats, totally deprived of sleep, will invariably die within 2 to 4 weeks. We don't currently have a definitive answer for what the function of sleep is, but one that's been the subject of a lot of research is the critical role it may play in memory formation. Just like sleep, memory can be subdivided into two different systems. Declarative memories refer to memories which are consciously recollected, such as semantic memories for facts or episodic memories for events. Declarative memories are reliant on an area of the brain known as the hippocampus, a seahorse-shaped region located in the brain's medial temporal lobe. Non-declarative memories can be accessed and recalled without conscious awareness, such as in skill learning or conditioning. This type of memory isn't reliant on medial temporal lobe structures, but on other regions like the cerebellum. We're more interested in declarative memories. Memory function also exists in different states. Encoding, the formation of a new memory trace. Consolidation, where labile memory traces are stabilized for long-term storage. And retrieval, referring to the accessing and recalling of a memory trace. A problem that's faced memory researchers is the stability-plasticity dilemma. This refers to how memory systems need to reconcile two competing functions of memory. To be plastic enough to enable for the formation of new memories, yet stable enough to maintain long-term memories. The largely accepted solution to this problem is what's come to be known as the two-stage model of memory. As James McClelland and colleagues in 1995 would theorise, memory traces come to be transferred from the hippocampal memory system over to a processing system involving the neocortex. The hippocampus and its related regions account for the plasticity function, whereas the neocortex and its related regions account for the stability function. The hippocampus is thought to teach the neocortex, with each reinstatement of a memory trace in the former expected to decay over time, potentiating such in the latter. Since the hippocampal memory system is important for task performance, it's been proposed that much of this reinstatement must take place in contexts where task performance can't be affected, such as during our sleep. As Jan Bjorn and Ines Wilhelm wrote in 2012, enabling memory formation could, and I quote, be the function of sleep that eventually helps us to understand why sleep is associated with a more or less profound loss of consciousness. In 1994, Wilson and McNaughton studied place cells in the hippocampi of rats. They found that the cells active as the rats learned a spatial behavioural task that involved navigating a maze were active again and in the same order during the subsequent night's slow wave sleep. Many studies since have found that in human sleep, slow wave activity enables the consolidation of declarative memories, and that REM sleep enables the consolidation of the non-declarative procedural memories. Why is this? One theory, the active system consolidation hypothesis, suggests that during slow-wave sleep, declarative memory consolidation is facilitated by the reactivation, redistribution, and integration into existing systems of knowledge of new memory traces, and that components of slow-wave sleep make this possible. These components are slow oscillations, sharp-wave ripples, and thalamocortical spindles. Let's start with slow oscillations. These are brain waves of less than 1 Hz, or less than 1 oscillation per second. Sharp waves are, as Nicolaus Meyer and colleagues put it in 2013, short bursts of strong synaptic activation. These travel along hippocampal pathways and are overlaid with trains of high-frequency oscillatory ripples. During the upstate of the slow oscillation, declarative memories are reactivated in the hippocampus in time with the appearance of sharp-wave ripples and sleep spindles. The slow oscillations essentially act as a pacemaker, providing the temporal scaffolding that allows for the ripple spindle events, which enable the dialogue between the hippocampus and the neocortex. Since we know that slow-wave sleep is responsible for declarative memory consolidation, perhaps we can improve memory formation by manipulating our sleep. This is what Bjorn Rasch and colleagues attempted to do in a 2007 study, where they presented participants with smells as they learnt an object location memory task, and then once again during their subsequent slow-wave sleep. It was found that these participants had better performance the next day on the memory task than subjects who had been presented with no smells. Not only this, but the smells were associated with a greater activation in the hippocampus. This effect had not been found for procedural memory tasks, REM sleep, nor wakefulness. Nevertheless, the finding is well replicated and has also been extended to the use of sound stimulation. This technique has come to be known as targeted memory reactivation, or TMR. In 2013, Dr Ngo and colleagues, noting that efforts to actually potentiate slow oscillation activity had yielded limited improvements to consequent memory performance, developed a technique known as auditory closed-loop stimulation. This is a technique sensitive to the phase of the slow oscillation. In other words, the administration of a simple, previously unheard sound cue is timed to the upstate of the slow oscillation. This produces slow oscillations that would not occur ordinarily, boosting their synchrony with sleep spindles and improving overnight gains in a word pair learning task. Our study is among the first to combine closed-loop stimulation with TMR, which is to say using specific cues, as in TMR, but applying them in phase with the slow oscillation, as in closed-loop stimulation. The aims for this study are as follows. First, to examine the case for memory reactivation following TMR, for which it is hypothesized that, just as in previous studies, TMR will improve overnight performance for cued items over and above uncued items. Second, to explore the neural mechanisms in place during memory consolidation. We hypothesize the reactivation occurs time-locked to sleep spindles. Third, to examine the beneficial influence of cueing during endogenous or naturally occurring slow oscillations. We hypothesize that cueing during the upstate of the slow oscillation will outperform downstate cueing. And finally, to explore whether cueing one subcategory can aid the reactivation of another uncued but associated subcategory, for which we have no formal hypothesis made. In our study, declarative memory will be assessed using a paired associates learning task, where 120 active verbs, for example the word jump, are paired with one of 6 images. Each image represents a subcategory and are themselves grouped into 3 overarching categories. So we have object, scene and human as the overarching categories, and belonging to each we have guitar and car for object, house and corridor for scene, and face and hand for human body part. Each image is paired with a semantically related sound. A guitar chord, a car ignition, a door squeak, a vacuum cleaner, a kissing sound, and a round of applause, respectively, and these will serve as the auditory reminder cues during the closed-loop targeted memory reactivation when the participant sleeps. Before that though, participants are first familiarised with this screen, featuring the images and their paired sounds so that these associations are made before the encoding phase. This is then followed by an immediate test, where 60 of the encoded 120 verbs are presented in and among 30 new words referred to as lures. This retest requires several responses. The participant first has to decide if the verb is new or old, and this will examine item-specific memory. Next, they give a confidence rating for this decision on a 4-point Likert scale, 1 indicating that they're not confident and 4 that they're very confident. If the decision is made that the verb is old, which is to say previously encoded, participants are then asked what category of image it was paired with. And finally, which subcategory the paired image belonged to. For this, participants are instructed not to guess. While the old/new response depicts recognition memory, the final 2 responses will assess associative memory, which is associated with hippocampal activity and by extension sleep. The delayed retest is administered in identical fashion to the immediate test, using the remaining 60 encoded verbs untested during the initial retest, with 30 new lures. During the memory tasks in sleep, continuous EEG recordings will be made from 64 channels located on this cap. And these measure neuronal electrical activity. In order to detect artifacts in the polysomnographic recording, eye and muscle movement will be measured using the electrooculogram and electromyogram, respectively. All participants will spend a night's sleep in the lab before the experiment in order to acclimatise to the new environment. Then, on the experimental night, participants will arrive in the evening. Once EEG and polysomnographic preparations are made, they then complete the memory task and get ready for bed. From here, they're then allowed to sleep from 11 p.m. until 7 a.m. Good night.
Good night.
At 7:30 the next morning, we then take a couple measures to test her alertness before completing the delayed retest.
When the participant enters slow wave sleep, we begin stimulation by playing sound cues through headphones reinforced to the ears with tape. The volume of auditory cues will be individually adjusted to a level the participant is comfortable with during wake, and we begin stimulation at a low volume and make step-by-step increases until an evoked response is observed. The cues are all matched in terms of salience, pitch, such that it's unlikely to wake the participant, and duration, lasting 500 milliseconds. In addition, a control sound of an artificial nature will be administered, sharing the same qualities. Across the night's sleep, closed-loop TMR will be applied randomly as either up or downstate cueing, meaning one subcategory is cued during the down-to-up transition, which equates to upstate cueing. For example, the upstate cue might be the guitar chord for the objects category, and a second subcategory belonging to a different category during the up-to-down transitions, or downstate cueing, so for example, the vacuum cleaner sound for the scenes category. The 2 remaining subcategories for these first 2 categories remain uncued, in this case the car ignition and door creak sounds. The remaining 3rd category, serving as the control, remains uncued altogether. So in this instance, that's the human body part sounds. Interspersed randomly will be an unlearned control sound during both up and down states. Closed-loop TMR utilises the brain interface software OpenVibe, and this allows for real-time EEG processing. The online detection of slow oscillations is based on the readings of a prefrontal channel on the EEG cap, filtered between 0.3 and 4 Hz, which is to say slow wave sleep, and this is designed to automatically deliver cues occurring in time with either the slow oscillation positive or negative halfways, which equates to up and down state cueing respectively. After each cue, the algorithm pauses for 8 seconds to give the brain time to respond to the stimulation.
If you found this video interesting and would like to learn more about how to be involved as a participant in a research study like this one, please visit www.memorybeham.com or www.memorybham.org. staresinalab.com, for which you may even be able to be paid for your participation. Thank you for watching.